Hey there, in this video I want to talk about solving simultaneous differential equations. Turns out if we were careful when we wrote our Runge-Kutta function in an earlier video, we really don't have to make very many changes here. But let's not get ahead of ourselves. So first, when I say simultaneous equations, like what does that look like? So let's do two equations here. Let's say one of these equations says dx dt equals some function of x, y, and t. And then we have another differential equation that says dy dt equals some slightly different function of x, y, and t. And so these equations are coupled to one another, and to solve, you have to solve the entire system of equations. Now the trick here to make this work out for us is we think of not of separate equations with x and y, but of a single vector equation, a single array equation that we could write, say like this. So we have d, and then let's make this boldface. The math BF there just makes it boldface. So that r would represent a vector for us, dt, and that's equal to some function of vector r and t. And if you can't read the matrix code here, render that, but we can actually see it. There we go. So the idea here is this dr dt is the exact same information as above, but r is an array for us now. And so we should be able then to use our existing Runge-Kutta code, except that instead of having x's and k's, we have r vectors and k vectors. So I have this already typed out. I'm just going to copy and paste it here because it takes a while to type it all out nicely. And I need to make that a markdown cell. All right, so basic idea is this is just our fourth order Runge-Kutta code, but we're going to make these things be arrays all the way through. And in fact, the code you wrote probably already will work with arrays. Try it out. And just in case you never did get that part working, here is code to do the fourth order Runge-Kutta, or a single step of it, written in a way that will work with arrays. So we don't need any special syntax here for x to be an array. If it is an array, when we pass it into the function f, if f was written to accept arrays, it works just fine. Let's try it out. Let's do something simple, like something that should make a circle. So I'm thinking like dx dt equals cosine y, dy dt equals sine x. And the hard part of solving a problem like this is just writing the function f to make sure it works nicely with arrays. The rest of it will be basically the same code we've been using with Runge-Kutta and with Euler's method. I mean, it all has basically the same structure. So anyway, coming back to the function we want to write, we want the first argument here to be an array. So we'll use just an r here to remind us that it's multiple vectors, or multiple values packed into a single vector. And the first thing we should do here should actually be to take apart those values. So we can use unpacking here to take the array of values r and split it into individual pieces, x and y. And then we can have our code here that includes fx and fy, which are the right-hand sides of our equations from up here. So in other words, they're the derivatives. So like I was saying, I'm picturing something that'll make a circle. So let's make this one cosine y, and we'll make the other one sine x. And then if we plot x versus y, it should make a circle for us. So this is our dx dt, and this next line here is our dy dt. Now we need to return our results. Here we have to be a little bit careful. We need to make sure our code works with arrays, so our return value here has to be an array. And that array includes fx and fy, so the two values in here. If we had three simultaneous equations, what would change? Well, we would have x, y, and z on this first line. We'd have to add another line to get dz dt after these two. And then our array here would just have to have a third term in it. So now that the function is defined, the rest of the code looks about the same as before. We pick some step size. We want an array of time values. Usually we'd make this with an a range because we know our step size here. It's just a little bit more convenient. So I'm going to go 0 to 10 in steps of h, and that'll give me a total of 100 values here. And we'll make h smaller if we need to. I want to make an empty list to store my x values, and I also want one to store my y values because I have both x's and y's I want to keep track of this time. We need to set our initial conditions. So let's go with 1 and 1. I'm just making up stuff here, but these are our initial conditions. I don't think it really matters too much. It's going to be a circle pretty much no matter what we pick for initial conditions. And then we're going to do a for loop. So for t in t values, first thing we do is append the old values of x and y. So we're going to append x, and then we'll append y. And then we're going to update x and y using our Runge-Kutta step function here that takes, that is the first argument f. For the second argument, it wants stuff packed into R that can be taken apart. So if I want x and y, that's what I should put in here. It doesn't really matter if I make these a tuple or an array. Python will know how to unpack them. We need t, and we need h. Okay, so not very much has changed on this line. It's just we are giving it a pair of values, and we are receiving a pair of values. These will actually come out as a single array, but if I want them separate to be appending them, then I need to make sure I've taken them apart at some point. And that's it. That is the solving method. After that, we can just make a plot. So I've been saying that this should be a circle. Let's check if that is actually true. So if I plot x values versus y values, and let's make it a scaled axis just to check if it's actually round. And then we show it, and it yells at me. What's wrong? PLS. Oh man, the very last line. Messed that one up. Yay, look, it's a circle. Hooray. And it's not centered at the origin. That has to do with our initial conditions. So we put x and y equal to 1 for our initial conditions, and then we just went from there. So I mean, I guess actually we'd start the circle at this point here and then go around. In fact, if you look really closely, and I'm not sure how well this will show up in the video, but you can see the line here is like a little bit darker. We actually have some overlap. Like we've gone around the circle more than once. And so I suspect if we make this points, that'll be a little bit, no, it's not that much more obvious. You can just barely see it here. If we start changing our t value, so if I made that like 5, there you can see here's where we start, and then we go part way around the circle. We didn't have enough time to go all the way around the circle. Okay, so as we've seen, working with Euler's method versus Runge-Kutta method gives you basically the same structure for your code, where you have h's and append values and updating them each step. And single equation versus simultaneous equation is also very, very similar. The only real difference here is just keeping track of multiple values, doing some tuple unpacking here, or actually really array unpacking here, to split them apart, putting them back together as you put them in. Just make sure you keep each value as you go.